Welcome back to Think Design Work Smart. I'm Alex Bolboaca and I'm coming at you from the Mozaic Works studios, and what I have for you today is an answer to comments from one of our previously published videos, which is 1 year old, but attracted a lot of attention and a lot of comments. And I've answered the comments, most of them directly on the YouTube page, but I think we can dive a little bit deeper because the topic is quite interesting and important. The video in question is NSA deems C++ memory unsafe, published 1 year ago, and it was basically following a paper by NSA. A paper in which NSA recommends using memory safe languages and excluding C++. And back then, Bjarne Stroustrup had a reaction, and they activated something called the direction group, and they started looking at using static analysis tools, and it was a lot of work there, a lot of reactions. Honestly, I haven't heard a lot about this since then, but either way, it's interesting to see what are the reactions in comments. And let's look a bit from the beginning. Like David Schmide, who was one of our guests, was one of the first to comment and said, yeah, your recommendation nailed the true security issue. C++ is simply too big and too complex. If you really want to use it, then you must be able to define a subset of features. The DoD should just rewrite everything in Ada. That was the original idea, problem solved. And I looked at Ada back then, and I remember finding it quite interesting for type constraints, which is something that I'm missing in modern programming languages. I'd like to be able to define a type, like for example, an integer type, but only with values from 1 to 10, or from 1 to 12, or from 1 to 99. So basically what I would really love is the ability to take an existing type and say, I want this type, but with these constraints. Another example would be a string type, but only with maximum length 45 and immutable. So you cannot change it. You create it and then it doesn't change. Things like that. And there are some ways of doing this, and I think C++ is kind of moving in this direction. But the reality is that there's a lot of existing C++ code, which will probably be very difficult to switch to these kinds of constraints. The next one is Jupe Staten 2328. NSA probably dislikes C++ because it is safe. They should know they've been reverse engineering and hacking software for years, including with their work on GitLab. C++ binaries are the hardest to reverse engineer. C# code basically falls open the moment you poke at it. Obviously, they would prefer a world where forensics are made easier for them, and therefore they will recommend C# in Java. And I thought initially this was an interesting point. Now, it sounds a little bit conspiratorial. On the other hand, there's no denying that NSA, their activities around security, and part of security is making sure that some things are secure, but part of it is also making sure that you can breach into some things. So it's not completely unlikely that this is correct. But so it's hard. It's more like your own judgment here. From my point of view, I tend to not be that conspiratorial. So while there is maybe a case to be made for reverse engineering easier certain programming, well, the output of certain programming languages. I think that in this case, I've done some reverse engineering in C++, and with the proper tools, you can actually do a lot of things. Okay. So, yeah, maybe it's a bit harder, but I can't imagine that there are no tools and there are no ways for dealing with this. Yeah, it seems more like there are problems with C++, and it was weird to me that some of these problems were not recognized by commenters, by some of the commenters. But yeah, there are some issues, and there have always been with C++, one of them being pointer arithmetics and everything that derives from that, like strcpy, string copy, which you could do in a very bad way, and you could create out of, you could get out of your process memory, and there were countless situations of vulnerabilities due to these types of constructs. Now, it's true that in modern C++ you can avoid these, but let's not forget there's still a lot of C++ code out there, and I'm not sure how much uses these newer, safer constructs. So while it's possible, I don't think it's the main ingredient. It sounds more like a defensive move rather than, let's say, an offensive one. But who knows, right? It's possible. I would give it like a 15% chance, but yeah. Right. The next one is by Riley T. Depp. LOLs, there's no such thing as memory safety, as the same as there's no such thing as safe system at all. As long as it's digital, nothing you can do with 100% safety on it. It's just a matter of strategic moves and rewriting if you want to achieve this safety security temporarily and come back again for another rewrite. My educated guess is that Google and Microsoft are targeting Linux systems and want to dominate server world too. Why in the world Linux is far more secure compared to Microsoft when it comes to servers OS? At the end of the day, every system and application are converted into bits and bytes for the computers to understand the instruction given. So there's no such thing as memory safe programming at all. And this answer conflates a few things. I would have to unpack this comment. Because there are a few statements, a few assertions into it, and I like to discuss each of them separately. Let's start with Google and Microsoft targeting Linux system and wanting to dominate server world. Maybe, although to be honest, Google and Microsoft benefit a lot from Linux. They run a lot of infrastructure on Linux. Android was built on Linux. Microsoft servers, the cloud servers offer Linux. And the stance with Linux has changed a lot with the CEO change since Satya Nadella came as a CEO for Microsoft. So would they like to sell their own things? Yeah, probably, because they are corporates and they want to sell more. That's pretty obvious. And who wouldn't as a company? But at the same time, they are using these systems. And then the next question is, what is the connection between Linux and C++? Because most of the Linux kernel is written in C. This was a very long discussion with Linus Torvalds. Very long time ago, he still wanted C and not C++ and nothing else. And as far as I know, now they are building some of the parts of the kernel in Rust. So it seems that they are moving in the direction that I was seeing in the video, which is instead of moving to C++, maybe many organizations would move to Rust. In this case, it's an open source. They kind of do what they want, and they have this privilege of, being very successful and a lot of people depending on them. And so they kind of use the technology that they want. And, C and Rust, this is what Linux is right now. Of course, on top of that, you have a bunch of C++ programs, but you also have a bunch of Python programs. And so, yeah, if you look at the whole ecosystem, yeah, absolutely, there's a fair number, well, quite a lot of C++ code in a Linux server. But also, Google and Microsoft would probably love to have fewer security issues. So there's also a hard, beyond all the commercial things, there's a technical thing. Right? There's a technical need for these all the systems to be more secure, because they are spending a lot on security, and it's annoying dealing with that things. Ideally, you'd have more secure software and you'd care less about that, and you'd have some automated systems and so on that could take care of running the whole thing for 90% of the time, and the rest is people dealing with it. But then let's move to another assertion with there's no such thing as the memory safety, as the same as there's no such thing as a safe system at all. So yeah, no digital system is 100% secure. By the way, no system in general is 100% secure. Your door lock is not 100% secure. And the reason why door locks work is because we also have a system around them. Like you have a culture of not stealing instead of a tribal culture of I can take whatever I want from my tribe. And we have laws, and we have police, and we have enforcers. And this is why locks work, because they are part of a more general system. But if you just take locks in separation, of course, you can break them. Any lock can be broken. And of course, there's no 100% digital system, and we are not talking about that. We are just talking about reducing the potential vulnerabilities by reducing the potential for programmers to make mistakes when writing their code. All right. And then there's a problem talking about memory safety, because memory safety is a specific thing. It doesn't mean security for everything. It just means safety in dealing with memory. I mentioned pointer arithmetics. In some versions of Windows, I think in Windows 95, Windows Millennium, you could basically use various tricks to take over the desktop. You could use pointer arithmetic to read data from another process that was running So there were all kind of things that you could do, and this was bad. And let's not forget that in some cases, I think, I'm not certain I remember, but it's not unlikely that you could actually use pointer arithmetic to write into the memory of another process, which means basically you could change another process while running, which means that you could change what it was running. Okay. And if this doesn't sound to you like a huge security issue, well, I don't know what is. Because at least, let's say if you have something installed on your computer that is, well, let's just imagine you have one of the modern social media apps and they try to find out more about you. Well, they could easily go into your calendar application memory, right, or the executable, and kind of rewrite it. And it would send all the data about your calendar information or your contacts or from your email application to a social media provider. Would this be legal? No. But would we want this to be possible? Obviously not. In terms of technical things, we want to restrict this. So, okay, this is an extreme example. It's most likely it doesn't happen today in modern operating systems, and that Windows, Mac OS, or Linux, Android, iOS. I don't think it happens anymore, unless there are bugs. Okay, but that's a different story. So when we talk about memory safety, it's about how many checks a programming language does on memory-related operations. So yeah. And the answer to this was, thank you, I appreciate that you got some of my pointers. As for the programming languages, strict guidelines should be implemented and must be followed to minimize, if not totally eliminate, the problems concerning the usage of memory and other resources. And no programming language is accepted on this matter. It's like continuous support and product patching until the product cycle ends, much like all Linux engineers have been doing ever since. And I agree. It would be great to have a strict set of guidelines. Well, let's be honest. Problem with guidelines is that the more guidelines you have, the more likely it is to ignore one of them by mistake or because you don't have time, or so we need some more support from the tools that we are using. And now, does this mean that every programming language should have all the possible checks in the universe? Probably not, because occasionally you need to do certain things that are, on the edge. But one thing you could do is to have those check in place by default in the programming language, and you can turn some of them off as a programmer if you really need to, and then maybe you also get a warning saying, okay, you turn this off, and even when running a program, maybe you get a warning somehow. So you could integrate this in various ways, but the thing is, yeah, it's great to think of programmers as these perfect beings who will follow instructions to the letter and guidelines and will know precisely what to do with them. But that's not true. We make mistakes. And if you give us 50 pages of guidelines or 15 pages of guidelines, it's already too much. We'll almost certainly make a mistake at some point. Okay. And then you might add additional checks like code reviews, static tools, analyzers, and all these things, which is great, but you also want us to deliver things very quickly. And then these things start to clash, and this is how you get bugs usually. Okay, so it's better to have a system that by default gives you safety, or as much safety as it's possible. Of course, we realize nothing is 100% safe. Then to have a system that is unsafe by default, and then you have to work to maintain it safe. And that at a certain level, this shouldn't be the job of programmers anymore, really. I mean, this might sound controversial, but look, we want to solve problems for users. And the people who build programming languages and compilers should want to solve problems for programmers. And that's how things are. And talking about safety, I know in C#, where you have memory safety, and there still are ways to abuse that. You have to work more, and presumably it's easier for static analysis tools to catch those, but you still can if you want to. So, and I find this weird with programmers, like there's always this tendency to go to the extreme case and take the extreme case and say, well, you know, there's no such thing as memory safety, so, you know, don't give me anything safer. Why? You only find its real work if you struggle to maintain a system running instead of actually building new features. You know, this is something I don't think I'll ever understand. It's a bit weird for me. Okay, and then another answer from GTD Coder. Yes, that is true. I mean, why not just design the machine instructions in such a way that it is impossible to write any software on the machine that would crash or have security vulnerabilities? Why is it solely the responsibility of software? And the answer is such a machine will no longer be a computer, no longer a general purpose machine. It would be completely safe, but also highly restricted in what it can do. Lower level languages cannot guarantee safety without losing the expressibility and flexibility of the language. Safety has to be guaranteed by the way the language is used and the environment in which it is used, not the language itself. So, yeah, and actually here we gave an example. The thing is with this, there are some machine instructions, and modern CPUs have introduced more and more checks and double checks on safety. Unfortunately, sometimes they have to deal with performance, and this is where you have the CPU bugs, which are a big pain, right? And those are really bad because of the only way to change them is to basically change the CPUs, which is fairly expensive to do. So again, I don't believe this. So, and let me read the answer that I gave back then. Based on what I understand about this huge topic, there seems to be a trade-off between security in programming languages, performance, and functionality. More checks require CPU cycles, and more restrictions. These allow specific use cases for system languages. For example, could you write a device driver or a bootloader with all the checks in place? And this is a kind of the edge scenario that I was talking about previously. In certain situations, you might need to do certain things, right? And that's where things go muddy. But one thing you can do is to have by default the checks in place and then turn them off. I assume it would be difficult if not impossible in certain situations. However, the secure by default principle should be followed in general purpose programming languages with the ability to turn off some of the checks. A simple example is immutability. It is a great way to write most programs and it helps remove a lot of potential bugs, which is why it should be the default in programming languages. But we need to be able to turn it off occasionally for specific parts of the code to allow for performance improvements or even implementing features that aren't possible otherwise. Another option would be to separate languages by goals or maybe have different profiles for system development, application development, server development. So, and I stand by these two options. So either have safe defaults and then you can turn them off. And I think Rust does this. Everything is immutable by default, but then if you really want to, you can work a little bit harder and do mutable variables. And another option would be to have your compiler configured for different profiles. So maybe I want to compile for device driver, which means, okay, the system development checks need to be turned off. I'm on my own, let's say. Or application development. I'm building an application. I'm building maybe a server and so on. In this case, you'd have different profiles with different checks turned on and off. And I think that's a perfectly reasonable way to deal with, but I'm not a language designer, so I may miss some things here. All right, and then Stephen Howie 4107 said there is a 5-man special group part of ISO C++ that is looking at how to improve the security of C++. Bjarne Strustrup is one of these. Last week I was at the ACCU conference, UK C++. And I met one of the 5. I asked, have you got much further in solving the security issues? And he said, no. There is one thing they had done. ISO C++23 defines span stream, and that was discovered. elect.add member function without bound checking or access. So this will be added in ISO C++26. There's also a paper, and it has been through a revision. So yeah, I'd be curious to go back to this. I haven't, but I don't know how far they've gone. If you know how far they've gone, let me know. And then a few days ago, like 2 weeks ago, VV78 posted a bunch of comments, which I haven't had the time to read and not even to often not to reply. So let's read them together for the first time and let's see what we can reply. Any software written in memory in secure languages potentially contains some bugs. They can be either the result of poor quality programming and design flaws or the result of special additions to the code of open source projects. Estimating the number of bugs is difficult due to the diversity of each project's source code and the unclear definition of what is and is not a bug. Different sources give different quantitative data on the average value of errors per 1,000 lines of code. Okay, so we basically start from the number of bugs that are potential in a programming language. Now, here's one thing that I take as a rule of thumb for the number of bugs. The larger the number of lines of code, the larger the likely number of bugs it is. So this is why I prefer to write fewer lines of code or to reduce the number of lines of code as much as possible, because in my mind, if we do that, it's unlikely that we'll get more bugs. It's more likely that we'll get fewer bugs. So now, somebody will come and tell me, but you can actually introduce more bugs but having fewer lines of code. I'm sure you can. I'm sure you'll find a way to do that if you really want to. But the natural thing that will happen, I think, the least code you have, it also easier to read through it, easier to understand it because there's fewer lines. And so two things happen. One, the density, you have fewer chances of introducing bugs because there are fewer lines of code. So just the statistical, let's say, naive statistical way of thinking. But the second one is because there are fewer lines of code, they are more manageable to our brains, which means we will be more likely to find potential issues. It is not the specific number of errors that is important, but their presence. Not every error can be exploited. However, even one single error lost from the eyes of developers in millions of lines of source code on a large project can be successfully used by attackers to intercept control of the system and then execute malicious code. Absolutely. So this is a big problem that you might not realize, and it's becoming bigger with the increase in security attacks. And that is, the more bugs you have, the more likely is for one of those bugs to be used as an exploit. So we need to pay attention. Write tests, people, write tests, and learn to love writing tests. I love writing tests. The way to do that is to write tests first, by the way. Test-driven development. At least test first is not test-driven development. Programming errors or special bookmarks are especially dangerous due to the fact that a huge number of digital systems simultaneously work with identical software and can be attacked en masse. Yeah. So if you have one error in one program that is very successful, it will just replicate to millions or maybe billions of locations. Identical executable files of the most popular software run on millions of computers facilitate large-scale exploitation. The same attack successfully hits many targets. Diversifying transformations are those transformations that change the internal structure of the program in such a way as to obtain a large number of different copies of it, different from each other but functionally equivalent. Interesting. So basically what I think is hinting at is that you could compile like in a different way so that each copy is slightly different and then the exploits work only on a single copy. That's very smart. That's actually the way genetic diversification works. Yeah, it's very interesting. Okay. A diversified population is a set of different copies of a program obtained through diversifying transformations. Diversifying transformations allow you to get away from the monotony of software. Good writing, good style. I like it. The requirement that the programming language's memory model must provide reasonable guarantees to the programmer sounds extremely informal. Let's try to formulate more specifically. Obviously, the programmer must have an idea of how the program he is working on behaves, and the behavior of the program is precisely determined by the memory model. As a consequence, it is desirable that the memory model be as simple as understandable as possible, and there be formal tools for reasoning about programs within the model. Simplicity is a very subjective criterion, especially when comparing weak memory modules, whereas the availability and expressive power of analysis tools can be used to more accurately compare models. There are various methods for analyzing programs. Among them, it is worth noting the methods of model checking and Hoare logic transformations. All right, look, I've heard about Hoare. I've heard about Hoare logic. I'm not an expert in these things. So right now, these things are kind of flying above my head. Well, let's see if I can understand more. There are also works devoted to weak memory models. The letter notes that if the memory model allows scenarios from the behavior of the program with the so-called out of thin air values, then a class of properties that can be checked or proven for programs with such models is significantly limited. Particularly the C++11 memory model allows such scenarios. What are the meanings out of thin air? Unfortunately, at the moment, there is no exact definition, but there is a set of examples of such behaviors, as well as the following sign of the presence of meanings out of thin air. Oh boy, so this is a lot. Basically, what I understand from this is that there is some literature and there's some research and some tools around two types of memory models. One is weak memory model and the other one is probably strong memory model. And for a weak memory model, then a class properties that can be checked is significant. So for weak memory models, you are very limited in what you can check, but for stronger memory models, you can do some specific formal reasoning, which I guess could be automated, and part of it is model checking and or logic verification. Whatever these things are, I'll have to read more to understand them. Okay. Number 2 from VV78. If in a script for the behavior of a program in which there are no arithmetic expressions, a certain value appears. For example, this value is assigned to a variable or written to memory, and this value does not appear explicitly in the text of a program, then such a script has meanings out of thin air. Okay. Scenarios of behaviors with meanings out of thin air always have some cyclic dependence between the values found in them. The fact that some models allow such scenarios is usually the result of the fact that the approach chosen to specify the model makes it difficult or impossible to disable out of thin air values without disabling the desired optimizations. Recently, automatic detection of errors in program codes have become an integral part of the modern software development process. To increase the safety and reliability of programs, you need to find and eliminate as many errors as possible, ideally in the early stage of development. For search of a rule, a set of analysis and testing methods is used, complementing each other. Static and dynamic program analysis, deductive verification, fuzzing, penetration testing. Buffer overflow is a situation that occurs during program execution as a result of accessing an array at an index that has a negative value or exceeds the size of the buffer itself. This error is especially critical in the C and C++ languages. An unpleasant feature of errors when working in memory in these languages is that the occurrence of such an error often does not lead to immediate consequence, such as, for example, crashing the program or generating an exception. On the one hand, this makes it difficult to test and debug programs because observed anomalies in program behavior may appear much later than the actual occurrence of the error or may not appear at all. On the other hand, the presence of such a defect can lead to the appearance of an exploitable vulnerability in the program, allowing an attacker to cause a denial of service, gain access to sensitive data, and even seize control of the attack device. This is what I was talking about. So when you have buffer overflow and there are no memory checks in the operating system, you could presumably read data from another program or change an existing program. Now, if you have let's say a program that runs with administrative rights and it has a buffer overflow issue, you can sometimes inject code that goes into the executable part of the process that will run as the administrative identity, which means it will have access to everything that an administrator has. Okay, so these are some things we need to care about. Let's read some more. I'm still not sure where this all goes. Moreover, according to the language standard, if the calculated pointer does not contain the address of one of the array elements, goes beyond the boundaries, then dereferencing such a pointer will lead to undefined behavior. Yeah. Thus, to determine such an error, the analysis tool is faced with the task of determining for each dereference point the size of the array and the value of the pointer offset relative to the beginning of this array. Based on this, the study of C-family programs in the context of information security is of particular interest due to the presence of a wide class of software defects associated with manual processing of memory objects, which is what I've been saying until now. An attacker could exploit errors in the handling of memory objects, which could lead to the compromise of sensitive data, injection of executable code, or denial of service. Yeah. So buffer overflow is one class, but there were multiple classes of such errors, which were very possible in C++, particularly with pointer arithmetic. All right. Programs written in the C family of programming languages are also subject to typical classes of vulnerabilities inherent in programs written in other programming languages. For example, errors in processing input data or the use of programming interfaces considered unsafe. According to the C++ programming language standard, undefined is the behavior of a program for which this standard does not impose any restrictions. The C++ programming language standard also states that the outcome of a program that causes undefined behavior is unpredictable. Thus, the result of executing an incorrectly formed program completely depends on the strategy for implementing the translation of the program code of the C++ programming language compiler, as well as on the environment settings of this compiler and the target program execution environment. The C++ programming language standard defines a set of incorrect language and semantic constructs that lead to undefined program behavior. A number of such constructions in practice do not lead to the manifestation of undeveloped software capabilities or can be corrected by the compiler automatically. In particular, such constructs can include program modules written in files without a new line character at the end of file, or declaration of user declarations or definitions in the standard std namespace, with the exception of certain cases such as specialization of template types of functions. However, some of the language constructs that lead to undefined program behaviors are translated into binary code, which leads to runtime errors. The class of potential errors that can be identified through textual analysis of program code in combination with analysis of the binary image of the program includes software defects in the program code that arise as a result of potentially unsafe optimizing transformations used by the compiler. In this case, it is advisable to carry out automatic analysis using mechanism for mapping source program code to the resulting machine code, for example, using specialized processor directives or debugger information. Moreover, according to the language standard, if the calculated pointer does not contain the address of one of the array elements goes beyond the boundaries, then dereferencing such a pointer will lead to undefined behavior. Thus, to define such an error, okay, so this is basically repeating, basically repeating the previous point. So, okay, so we have a set of undefined behavior, which, as far as I understand, is more difficult to check for, or we really need to check for, because we don't really know what the compilers are doing with it. Let's see number 4. According to the C++ programming language standard, undefined, okay, so we discussed about the undefined behavior. Depends completely, incorrect, okay. In particular, such constructs, okay. Advisable to carry out source. If the source code is unavailable, automation of the analysis of this class of potential errors can be carried out using tools for analyzing binary images of programs with the participation of an analytical group that determines the rules for automatic detections of typical representative of this class of software defects. In the C++ programming language standard declares the translation of the program code is carried out as is, the as if rule, that is, it should not change the observed behavior of the program. Thus, the optimizing compiler can carry out any optimizing information transformations of the program code that do not change the visible behavior of a program. Therefore, an optimizing compiler can apply dead code removal transformation to function calls that do not change the external behavior of a program. The dead code removal transformation eliminates store instructions that do not affect the operation of the function. When transforming assembler into railed representations, many instructions are created, the result of which is not used. Removing the dead code has several benefits. It reduces the size of a function and allows other types of analysis to avoid processing unnecessary instruction, thereby reducing the time of other type of analysis. After the transformation, a new function and a new control flow graph are created. A popular use of assembler is program optimization, that is reduction in program execution time compared to high-level languages. And then I guess it stopped. Oh, okay. But if you simply rewrite the test from example from C into assembly language, translating each command in the most obvious way, you often find that the C procedure runs faster. Okay, so now we are getting into we are getting into a lot of things. And okay, so I understand that it's better to have a stronger memory model. I don't understand how this relates to the C++ thingy. My guess is that the undefined behavior is one of the issues, and due to undefined behavior you need to pay extra attention to things. So this is a class of problems. Another class of problems is pointer arithmetics, and you need to pay attention to those. And then we are talking about optimization, which my guess is that, let me just try to read through this quickly. Yeah, he's mentioning memset, which is another, but this is a C library. What I don't like is that we are mixing C and C++, and these are two very different languages. So C, okay, it has its problems, but let's not mix those. We are talking about C++. So in C++, we have undefined behavior, we have pointer arithmetics. We need to use certain tools to figure this out. I hope that in C++ we don't use things similar to memset anymore. So let's see what was the final things. The final comment. Depth of information is fundamental benefit as a concept called virtual machine introspection. VM introspection is the study of the current state of the VM at the system level. For virtual machine introspection, the current state can be defined quite broadly, including information about processor registers, memory, disk network, and any other events. A fundamental problem of introspection virtual machines is the gap in the levels of representation, the so-called semantic gap. So by the way, I assume that when we are talking about virtual machines here, we are also talking about the environment in which a program runs, like the Java virtual machine or the C#, whatever it was called, virtual machine, the .NET. And that those are easier to analyze, have this introspection, easier than programs that run directly in the operating system, more or less. The fundamental problem of introspection of virtual machines is the gap in the level of representation, the so-called semantic gap. In other words, introspection is the extraction of data from the operating system that is used by the system for its operation. This data is hidden from the user. The technical component is a set of software functions and algorithms that provide an analytical component with data for analysis. This can be, for example, the bytecode of a file, text lines inside the file, a single program action within the operating system, or a whole chain of such actions. The analytical component is a decision-making system that includes an algorithm that analyzes the data at its disposal and makes a certain judgment about it. In accordance with this judgment, the antivirus or other security software takes the action is established by a security policy, notifies the user, sends a request for further actions, quarantines the file, blocks unauthorized program actions, etc. Modern antivirus protection tools, as a rule, simultaneously implement both technical and analytical components based on the combination of the listed protection methods. At the same time, despite the fact that the signature method is outdated, it still remains in security products and is advertised since it is part of a sustainable business model and users are also accustomed to it. However, do not forget that creating signature is a manual process of developing new signatures, and releasing updates to the user can take from several hours to a day. So we basically moved now into the antivirus and security software kind of things. Thus, we find the signature mechanism do not protect against new threats that have not yet entered the database. Due to the manual compilation of signatures, they give false positives. The database of signatures is growing day by day, and in connection with this, working with signatures imposing increasing cost on computer resources. As practice shows, the heuristic method copes only in a small number of cases of this approach. Also does not solve the problem of protection against the launch of malicious programs. With modern methods of hiding and encrypting the executable files, for example, code obfuscation, it is almost impossible to detect new threats using such methods. The described methods are using in modern antivirus products. Thus, by observing these and not only rules, you can make the system more secure. Yeah, I mean, there's one thing that I'm thinking about, which is after all these comments, these comments are very insightful, but I feel like they've gone in a bunch of different directions, and it's a bit hard to understand the whole idea. But there are a few things that I'm taking away from this. And I kind of like the fact that you could compile things in a different way and kind of generate, particularly for software that goes to a lot of people. And so that the resulting code is slightly different. The resulting executables are slightly different, and therefore they are slightly different. Well, they are resistant in different ways to exploits, let's say, even if you have an error. And that's an interesting idea for security. Now, people who are dealing with optimization will be very unhappy with this. But yeah, you need trade-offs. Another thing that would be interesting is the idea of sandboxes. And I've talked about on this channel about the fact that, what's the name? The WebAssembly runtime was created initially in order to be kind of basis for different programming languages to script browsers. So instead of having just JavaScript, you could have JavaScript, Python, Rust, whatever, and the interpreter and the thing would compile into WebAssembly, which is the thing that actually runs on the browser, pretty much like in an operating system. You'd have assembler and executable and compilation and all that. And it turns out that WebAssembly is an interesting technology because it runs in a sandbox by default, which means it is limited in what it can break, in what it can access. It has a natural border, which allows code to be written in a more secure manner. And this is something that I've seen, based on what I've read in past articles, that is used by different, or is explored right now by different organizations. And I'm really curious where it will go. It might also be a boost for Rust, because Rust is the likely programming language for low-level WebAssembly development. And if you want to do high-level, most likely JavaScript will still be there, but then maybe other languages like Python will also be used for kind of higher-level things. But if you want to do things where the memory matters or optimization matters, like maybe video games in your browser or various simulations, then you need something like Rust. You could do in C++, but most likely, I think, based on what I'm seeing, Rust is the language that will be used for this. And what this means is that this relates to the virtual machine talk that we were discussing, because if you have a kind of a sandbox, then it's easier to limit access, it's easier to monitor things, it's easier to check where things could go wrong, particularly if you have this type of introspection that VV78 was talking about. So that's an interesting thing. Or running on a virtual machine. But for C++, we want performance. We want to be as close to the metal as possible, as close to the CPU. And because of this, we'll still need to pay a lot more attention to the potential problems that can come up, particularly in relation with memory safety. And I think another thing that I take from here is that it would be useful to have stronger memory models, which my feeling, I didn't fully get that part from these comments, but I'm feeling that you could have the C++ memory management be done in a more predictable way, such as you could analyze it at runtime and figure out if anything bad happens. In addition to this, I'm also thinking about something else, which is, wouldn't it be nice for every program to have a kind of a list of things that they can access, that the program, it can access, that are as limited as possible, and so to limit the calls. And I think this is probably part of what they tried with Windows, but it would be more interesting to have it kind of as an automated system that keeps checking or keeps blocking things. And I think some of it is possible with AppArmor in Linux, but I'm not an expert in these things, and it's been a while since I programmed for Windows, so I don't know precisely if you can have now a kind of a security manifest that says these are the things that I'm accessing and nothing else. That would be nice, and the sandbox would provide this in a way like, so I'm trying to access something that the sandbox doesn't allow by default, And because of this, I'm getting a warning, and now I need to add something to the security manifest, which is also published. And an automated system can take care of it from the operating system. So that would be maybe another thing of combining different methods together to create more and to avoid these issues that stem from memory unsafety. But overall, let's not forget that it's still possible to write code in C++ that is prone to buffer overflow. And there's probably hundreds of thousands, if not millions, if not tens of millions of lines of code in C++ that are prone to this. So any conversation we have, we need to take into account the current state of the C++ code and how easy it is to move it towards a better model. No. So yeah, this has been very interesting. These comments have been very insightful, and I like this is one reason why I love comments. I learned something new from every one of them. So yeah, keep writing comments and let us know what you think. If you know more about these topics, definitely let us know. For example, horde logic, what it's used for, and please explain to us. I'm not sure I will have the time to check it out, but it sounds like a very interesting topic. With this being said, as usual, thank you kindly for the view. And until next time, remember to think, design, and work smart.